Hey everybody, welcome back to Tech Shorts and Happy New Year for 2022. I hope this is going to be a great year for everybody and, more to the point, for the world. We've had a lot of big news coming out of AWS in the last few weeks regarding HPC, in the lead up, particularly through supercomputing, reInvent, and then the lead up to the holidays. This is really the first opportunity we've had after the holidays to get together and talk about some of these bits and pieces. But in particular, a really big announcement, which is the new EC2 instance family, the HPC6 series, and in particular, the general availability of the HPC6a. So I'm joined today by Neil Ashton in Oxford. Hey, Neil.
Hello.
How's Fred, the dog?
I'm really hoping nobody comes to the door to deliver a parcel, because you'll definitely hear him. So,
okay. Actually, me too, because I forgot to go and give Elmo a bone. And Dr. Heidi Poxon in Minnesota. Hey, Heidi.
Hey.
Now, Neil and Heidi are the two folks internally who've had the most insights and most time to play with the HPC6As. We've got a bunch of benchmark data that we want to show off around some applications, some real application performance that we've done. And I think Neil and Heidi, your teams managed to get hold of, I think it was around about 400 droplets, 400 nodes in the, while we were building out the fleet early on. You got your hands on about 400 nodes and ran some fairly decent scale workloads up to around 38 or 40,000 cores. So we've got some interesting numbers to talk about in December. We talked about Graviton, some of the really weird things we had. Single sockets, but 3 sockets on a motherboard and some strange architectures for Graviton 3. And that wowed a lot of people. These machines these are AMD based machines, and they are dual socket instances, right?
Yeah, they're dual socket, and they're AMD's 3rd generation of their EPYC processors. So codename Milan, for those of you who are familiar. These instances are HPC optimized, so we really are focusing on codes that are tightly coupled workloads, tightly coupled applications, typically using MPI, that communicate between nodes, between instances often, so that they can achieve better time to solution and scale across lots of cores.
We went for 48 cores per socket. Now, we explored that a lot. Right, Neil? We looked at lots of different options for the CPUs there, and we came to the conclusion 48 cores was pretty good across the broad swath. What's the big factor there?
Yeah, well, I mean, the reality is there's a wide range of workloads that we have to cater for, and when you do that, you have some codes that are very kind of compute bound and will take the largest amount of cores per node that you can give them. And there are others that are extremely memory bandwidth bound and actually don't need that many cores. So really, we could have gone all the way up to 128, or we could have had a 64. And 96 really was the sweet spot, I suppose, of having both sides, where you've got some who will want to use the full node, take all the cores, and there'll be others who simply can take advantage of the large amount of memory bandwidth and maybe just turn off a few cores. So hopefully it right. kind of gets for most workloads.
Yeah, I mean, one of the things that I noticed from a lot of our early benchmarking numbers that were coming through, and when we do benchmarking, we always worried about real application performance, not synthetic benchmarks. But I mean, I was noticing that more of the codes were scaling well into the 96 core territory, and but after about 96 cores, things started to flatten off with some of the larger core count. Heidi, networking. It's a bit weird, right? Because there's 2 different networking numbers here.
Yeah, so to target MPI codes, to target tightly coupled workloads, we wanted to offer the 100 gigabits a second EFA. So this is the network throughput, high throughput, low latency network that we offer. We wanted to deliver the best performance for data movement between MPI processes, between instances, and also to make sure that your data through Lustre, your data movement through Lustre is also efficient. But we did, in order to offer the best price performance, offer the nice cost advantage, of these instances, we did dial down the networking bandwidth for any work, any traffic that's moving outside of your virtual private network, so your VPC.
Right. And so we've sort of built express lanes in the infrastructure to make sure that things like S3 and EBS are highly performant. But when you get outside that, if you're using TCP/IP traffic, you're going to see that you really are going to see probably the effects of the 25 gigabits. But most HPC workloads, the inter-node communication is going to be MPI. It's going to be heavily leaning on the 100 gig EFA adapters. And
right.
Now there's another weird thing here too. We're only offering these in single AZs in the regions where they're launched. Now they're launching in 2 regions first, but we're only offering them in single AZs in these regions. There's an element there where we're really HPC customers told us that they really didn't need to have capacity pools split across multiple AZs. They weren't building HPC clusters looking for massive redundancy like an enterprise customer would. So that seemed like a good way for us to actually pool and corral the resources into these AZs to see if we could achieve a higher utilization. And utilization is actually a big cost factor for us.
Right. And running within a single AZ, what that gives you is that gives you close proximity between your instances, which will deliver better performance as well. And so again, focusing on the tightly coupled workloads and allowing MPI jobs to run, MPI codes to run across instances very effectively and very efficiently. This was another decision that we made to keep things within an AZ.
When you build a cluster, the key advantage of AWS is it's not a HPC6a only cluster. You can have lots of different node types in this cluster. I mean, for example, the 6a I had for doing this stuff, one of them, I thought maybe I might need loads of RAM to do some decomposition. And I just had one of our R type instances, I think like an R5. I just put it in my parallel cluster thing. I had a GPU there just in case I need a GPU. So,
right.
You know what I mean? Like it doesn't preclude the fact that if you do need more than 384 RAM, and usually that's typically not in a scale up fashion, it's usually more like a pre-processing step. You can still pick one of our nearly other 400 instances to plant next to it.
Well, I think it's 475 instances now.
Yeah. Sorry.
Let's talk about some performance numbers, because we've got some good performance numbers, and like I said before, we look at a lot of different application domains when we look at performance. We don't really focus on streams, benchmarks, and MPI ping pong. They're only interesting insofar as they lead to a result, and the result is actually the thing that's more important, right? So,
as you said earlier, as we were building up the fleet, we grabbed some instances to play on, and so we did some initial runs. We tried to cover a few areas, so molecular dynamics is one of them, and LAMPS is one of the codes that we run typically. You can see here, we did do a performance run all the way from 64 instances up to 384, so a little shy of 400 instances for the problem for the input. And you can see the performance scales quite nicely with LAMPS, which is great news.
And on the cost side, of course, this is the big thing. And I think we forgot to mention this actually when we were talking about the specs. But let's talk about that. These things are 3 cents per core hour on demand. No commitment. You can just rock up from anywhere and just spin up a bunch of cores, 3 cents per core hour. Or 1.6 cents per core hour if you wanted to buy a bunch of them in advance on a 3-year savings plan. Okay, let's have a look at GROMACS, because it's one of the other big MD codes that a lot of folks run.
Yes.
Now, we've got a couple of different benchmarks here, because we've got one that's like a small model and one that's a large molecule model. So
yeah, we were looking for, we try to apply different model sizes, especially when we're doing scaling analysis. You have to have a big enough problem size if you're scaling to large core and large instance counts. But here for this particular problem, we wanted to make sure that we were seeing the scaling that was appropriate for these instance types and the network that's applied, the EFA network. And it looks like we saw some good results again.
Yeah.
So this is running on up to 16, and then you can see the next size here. We ran on a much larger.
Right. This is a much larger model, and we've actually done a lot of benchmarks on these with other instance types. And
Yes.
Austin published like blog after blog exploring this space with GrowMax.
Yes.
This is easily the winning price performance thing.
Yeah.
Across the lot, right?
We pick a few cases that people tend to want to benchmark, and we always say to customers, you don't have to believe the graphs we put up. You come on, you can try it yourself, you can run the codes. Many do, and they get the same results. And this is an example of the ANSYS Fluent, which is obviously one of the most popular CFD codes. And I think the reality is that there's always two ways of looking at it. Most people are running circa 100, 200 million cell cases, whether it's designing aircraft, cars, whether you're doing more manufacturing or wind turbines. It's probably around the sweet spot. And the point with the 6A is, one, it gives you a really nice turnaround time potential. The fact that you can be running on hundreds of nodes, so tens of thousands of cores potentially, does mean that you can turn around the jobs faster. Certainly compared to, if you look like, most of the customers I speak to, on average, they may only have access to maybe 500 cores, maybe 1,000. And these are not little companies. I'm talking like, OEMs. That's just a way, because they may perceive having a big cluster, but they've got like 5,000 engineers or something. So
right.
They're not really able to actually get access to it. So they can really push the boundaries, I think, with AWS. And then you're right. I mean, the cost is the single biggest one. I genuinely believe now, what are the bottlenecks left not to be moving to the cloud? I personally don't see. You've got the performance. You've got a really cheap on-demand price. I mean, there was always good price, with reserved instances, even with other instances. But I think what makes a big difference is that you can actually, even with no commitment, get a 3 cent per core hour, and then, as you say, get 1.5 or 1.6.
Like, let's keep talking on CFD, because Siemens star CCM is clearly a code that a whole ton of folks are using. What's the subtleties on this graph here?
Yeah, so C5N is probably the workhorse of most people doing CFD now on AWS. It's certainly the one I see, day to day. People are using, so that's why it makes sense as a nice comparison. And it's a great instance. It gives really good scaling performance. You can see it's still having a linear scaling on the graph there. But I suppose the key bit is again going back to the blockers. Some people sometimes perceive this idea that the cloud can only be doing smaller jobs. That once you go above 1,000 cores or 10,000 cores, that's in the realm of supercomputing centers. And somehow AWS can't do that. Now, this is a 40,000, approximately 38,400, whatever.
Yeah, it's a lot of cores.
I mean, that I've had access to most of the big machines around the world, NASA machines or in Europe, whatever it is. Very few people are even running 40,000 cores on those machines. Right. So I don't perceive many automotive manufacturers will ever need to go to 40,000 cores. But it's just the point that the infrastructure and the capability is there to do it. And I didn't do anything fancy for this. I ran the same star-CCM command that I use on any other case. I didn't have to do anything fancy with any tunings or settings. I literally just ran the case. And this is honest, I literally ran the case, changed the number of nodes, and that's it.
Okay, so now let's talk about weather modeling, because weather's a hard problem. It was often positioned to me as being the problem that AWS couldn't solve because we didn't have a low enough latency network and all of the other reasons why it couldn't be done. And now we're doing it regularly, a lot.
Yeah, I don't know. I can speak a little bit to Wharf, and then maybe Neil can jump into. Again, This is one of the codes that we typically run with our performance engineering team, just to make sure that we are seeing the expected behavior. This particular problem size, you can see how far it scales, and we were really pleased with the results. Again, as Neil said, it wasn't very difficult to run on HPC6a compared to the instance types that we've run on previously. There weren't any major surprises. It just naturally flowed. And so you can see here, again, we were able to run with a pretty significant core count, and we were happy with the results.
And these are, you know, getting into the tens of thousands of cores arena. This is what a real, you know, operational weather forecasting center is using on a daily basis. Let's also talk about DTN's model, right? This is an MPAS model, is that right?
Yeah. So, you know, I think the point with DTN is they're trying to do this high resolution weather modeling. So they need to run really big models, and they need to be doing it sometimes in a daily fashion at certain times, you know, to get forecasting windows. And they really need to do it at scale because these are huge models. You know, a bit like CFD, you need a lot of grid points. You need to do these really big simulations. And so it's a simple matter of you need more compute for the turnaround point of view. You know, there's always that argument of the ideal one is you throw more compute, you get it back in half the time, and you pay the same price. I mean, that's the kind of dumbed down version of linear scaling, isn't it? But sometimes a scaling graph can be seen as just like a marketing exercise, and you know that they're never actually going to need to run that many cores. But then there are scenarios like this when, for like the weather, they legitimately do run a large number of cores because the problem size is big enough and their codes can scale well enough. And as long as you've got a good enough infrastructure like AWS has with EFA, it actually makes sense. So this is an example of not just for the sake of going big. These are legitimately running big models all the time and need this sort of scale.
So here's the HPC6 landing page, and you'll notice the URL does say HPC6. In the first instance, it's an HPC6a. These are AMD-based instances. The A stands for AMD. You'll notice we've made a change with our nomenclature across the board where, you know, like, for example, when we introduced the C6i, which is an Intel-based instance, the I stands for Intel. So we've now got C6Is. You'll see C6As and the HPC6a. You'll see C6G and C6GM. The G stands for Graviton in that case. You know, this is a multiple CPU architecture approach. So starting today, the HPC6a over on the CFD landing page. We've got some examples there, some tutorials that folks can follow where they can deploy some of the workloads that you've described directly onto HPC6As following a tutorial and just get there really quickly. Right. Heidi, Neil, thank you for coming along today. Really appreciate the time. And for everybody else out there, if there's ideas that you'd like to see us cover on future Tech Shorts, please DM us. We do listen. We absolutely are watching that. Our DMs are open. We'd love to hear from you what other things you'd like to see us cover. And if there's areas you want to see us go deep into, you know, we'll absolutely get an expert along and try and do that. But for now, I guess thanks very much to everybody. We'll see you soon.
Love the teacher.